Look at any modern city skyline. Massive towers of steel and glass piercing the clouds. They look like permanent, immovable monoliths. In reality, skyscrapers are dynamic, moving structures. A glass of water on the 80th floor reveals this truth. Even in a sealed room, the surface ripples as the building moves. Wind serves as the invisible, relentless force driving this constant motion. The defining characteristic of a megastructure is an engineered illusion, stillness masking constant, necessary motion. As air currents strike and wrap around the exterior, they create intense pressure differences along the building's surface. These forces amplify with altitude, with higher elevations experiencing stronger wind speeds. Because these towers are locked into the ground but reach high into the air, they behave like vertical cantilever beams, an engineering model deeply anchored at its base but unsupported along its vertical height. When wind applies pressure to this cantilever design, the physical displacement happens almost entirely at the top. The base holds firm while the peak shifts off its vertical axis. Engineers refer to this as building sway. It describes the controlled displacement of a structure reacting to environmental pressure. Most modern skyscrapers are designed to safely move several centimeters back and forth. This movement represents a predictable, intended reaction to extreme vertical height. Curious, this raises a question. Why not design these towers to be perfectly stiff? A perfectly rigid building standing dead straight against severe wind cannot deflect the incoming force. It absorbs the blow entirely. That kinetic energy converts into internal stress, concentrating intensely at the structural joints. Over time, this trapped stress causes physical deterioration. Materials experience extreme fatigue, and microcracks form deep within the load-bearing supports. Faster, more urgent, those fractures spread, leading to total structural failure and eventual collapse. Engineers intentionally design flexibility into the architecture because a structure that yields survives where a rigid one would fail. Engineers must optimize and control this movement to keep the building stable. Massive counterweights are hidden inside the mechanical rooms at the very top of the tallest skyscrapers. This mechanism is a tuned mass damper, a heavy pendulum or block calibrated to swing in opposition to the building's sway. When severe wind forces the outer structure to bend to the left, the heavy internal mass violently swings to the right. That opposing motion safely burns off the wind's kinetic energy. It reduces the distance the building travels and brings the structure quickly back towards its vertical center. These massive internal systems transform a passive steel box into an active machine capable of neutralizing environmental threats. During a severe storm, occupants on higher floors may still feel some motion sensitivity or discomfort as the building works. That sensation of movement provides physical proof that the survival mechanisms are functioning. True structural resilience comes from a willingness to yield to extreme external forces, bending to safely distribute the pressure. Viewed this way, these monoliths reveal themselves as living, breathing entities, reacting to the sky. Skyscrapers survive extreme heights by moving with nature.